Okay.
So we already know that we can use cycles in order to produce power, okay? And we have seen in the course material several special cases, like, for example, the conventional Rankine cycle, a Rankine cycle with reheat. And we have seen that each time we try to do some changes in order to enhance the efficiency of the system, okay? So if you remember, what was the ideal system to use? The ideal case which can produce maximum efficiency?
The ideal reheat Rankine cycle, you mean?
Yes, you have the Carnot cycle that is ideal, okay? But the Carnot
Yeah.
cycle consists of two isotherms and two isentropic processes. And practically, it has some disadvantages because, first, whenever you operate with a turbine, okay, you need to avoid having a water droplet
At the
because
exit of
water
the
droplet
turbine.
will harm the turbine. So it's
Yeah.
not good to have an exit state from the turbine where you have mixture of liquid and vapor.
Yeah, the
Okay.
quality should be high.
Exactly, the quality should be high, and if possible, if we can
100.
reach the 100%, it is much better. Okay,
Yeah.
so this is one advantage of the Carnot cycle. Plus, also for the pump, it's also recommended to have complete liquid. Yani you don't have, we don't have. If we have vapor, this will also be harmful for the pump. That's why
Mm.
we come up with a new cycle. So first, the practical or conventional Rankine cycle will consist on having, if you want, we start, let's say, from if we pump from the saturated liquid. When we pump it from the saturated liquid, we elevate the pressure to another level. So here, mainly the function of the pump is to go from the low pressure to the high
The
pressure.
higher pressure.
Exactly. And after this, we enter the boiler. In the boiler, we have heat exchange at constant pressure. Okay. In the
Pressure.
boiler, this is where, if you want, we take heat. Let's say if we are talking about a power plant to produce electricity, at this level we have Qn, Q dot N.
Yes.
So heat will be taken, let's say, from combustion gases to the fluid circulating in the cycle, and we keep heating. It's good to heat more. Why? To get rid of the disadvantage of having low
Water
quality at the
droplet.
exit of turbine. Okay, because by
Yeah.
comparing with the conventional Carnot, when you if you leave at this stage, for example, or if you do more superheating, you can leave at the desired level, which is, let's say, 100% vapor, which is at the exit from the turbine.
Exit of the turbine.
But also, what is the limit here? We said that we
We
have high
exceeded the
temperature.
maximum temperature.
Exactly. So this is why we thought about another alternative, which is to do multiple reheat. So when I do
Yes.
multiple reheat, okay, I limit the increase in temperature, and at the
Well, mainly
same
it's
time,
to
I can have a high value for the quality. So all of these strategies enhance the efficiency of the system. Now, in this example, we'll see another strategy, okay? And always, let's say, if I have a new system, I will always give you all details. Yani I will tell you, I will explain for you how the system works, and then all you have to do is to apply on it the thermodynamic equations. Okay. So,
okay.
for example, let us say I am proposing the following cycle. I will tell you how the cycle will operate, and just you can, based on the explanation, you can draw the corresponding graph. So this cycle corresponds to the regenerative Rankine cycle, and we'll discuss together what do we mean by regenerative. Okay. So let us go over a small description of the system, then we'll go to the analysis of the different steps. So an open or direct contact feed water heater will be, which is basically a mixing chamber, will be added to the cycle. Okay. The purpose of this feed water heater is the following. In this heater, we'll have a part of the steam extracted from the turbine will mix with the feed water exiting the pump. Now we'll see what is the purpose of this. So in general, at the exit of the turbine, you take the fluid directly to the condenser, completely to the condenser. Okay, what we will do now is we will take a part of the steam exiting from the turbine, we'll take it into a heat exchanger in order to, if you want, to mix, okay, with another steam that is coming from the exit of the pump. Why we
هيدا
do this?
مثل cogeneration.
No, this is different than cogeneration. Look, cogeneration, if you want, it's a combination of different cycles. You can consider it's an internal cogeneration. Yes, you can say this. But in general, when we talk about cogeneration, you can combine, let's say, you can take heat from a system and supply it to another cycle. Okay, and you have, let's say, two separate, like in the case of steam turbine, let's say, and conventional and gas turbine. So you have the steam cycle, the conventional steam cycle. You have exhaust, and you want to operate this cycle. Okay, you know that for the conventional cycle to operate it, then you need to provide Q dot into the boiler. Okay, so this heat, if the source of this heat is from another cycle, like the gas turbine system, where you have high exhaust gases, it's an open system. Okay, in this open system, you have a high temperature of gases that you can profit off. So you can pass by these hot gases through the boiler of your conventional cycle, and then this is the process of heat recovery. So you are using waste heat from a cycle to operate another one. Okay, here, if you want, this is an internal cogeneration, if you want, because you will take heat, you will take part of the steam from this turbine, okay, to benefit from the relatively high temperature at this level, in order to mix it, okay, to mix it with the exit of the first pump. And here you have two stages, pump 1 and pump 2. Okay, and the purpose then, when we do the analysis on the graph, we'll see that this will lead to a higher temperature at the inlet of the boiler. And how we can benefit from this, do you think? So if I can increase the temperature at inlet of boiler, I can reduce what?
The pressure.
I can reduce, if you want, the input flow rate.
Droplet.
Okay, I should put in the boiler. Okay, so the idea is the following: if I use the conventional Rankine cycle, I don't have this. Okay, I have the fluid exiting the turbine will completely expand. Okay, will completely expand until this point. It will enter the condenser. Then we'll have only one pump, and this pump will increase the pressure from the low pressure to the high pressure, and will reach this state. Okay, now once we reach this state, the temperature will be much smaller than the case of regenerative Rankine. Okay, because whenever we do this, let's say this is point, if you want, I will call it point. It's a point that is not in this cycle. I will call it point Z. For point Z, the temperature is smaller than 0.4. And therefore, in the boiler, I will have to heat, I will have to provide a much larger value of heat. So here, all of this part, if you want, will be extra. So I should provide an additional heat, okay, compared to my cycle now. Because if you look at the figure here, okay, in the boiler, what you do, you will heat in this problem from 4 to 5. So if you want to calculate the amount of heat, you know that graphically the amount of heat Q is provided is integral TdS. So you can do some graphical analysis on this. You can see that the amount of heat in the boiler is equal to this part. Okay, however, if you don't have the open feed water heater system, then you have the following heat. You should heat from this level. Okay, so you are reducing this part You are reducing the energy consumption by using the system. Instead of, you will reduce the value of Q dot N, and you know that the efficiency of your system is calculated as W net
over
over
QN.
Q dot N. Okay, so from here, you can benefit from reduction of Q dot N to increase the efficiency. Okay, now, as calculation, how we can verify this by calculation? Well, first here, things are a little bit more complex. Why? Because we don't have the same mass flow rate circulating over the whole system. Since once you reach the turbine, and let's say you have the mass flow rate m dot, okay, when you reach the turbine, you have a portion, a certain percentage will go towards the open feed water heater, and another percentage will go to the condenser. And in general, this percentage can be optimized. Yani, what will be the best fraction to take in order to get the best performance? In problems, they will give us y, or it will be the only unknown. Yani, they will, in any problem, they will give enough information to be able to solve for the unknowns. So maybe they provide y, and then you have other unknowns to determine, or you have everything, let's say, and you need to determine y. So the idea here is that m dot will be divided into m dot. In general, we do the analysis per kilogram a second. Okay, so we consider for 1 kilogram per second, we have one part that will go to the open feed water heater, which is y, and another part will go through the condenser, which is 1 minus y. Okay, and then these two parts will mix again in the open feed water heater. So the feed water heater is simply a heat exchanger, if you want. Okay, but here you have two inlets for this heat exchanger and one outlet. Okay, so when you want, if you want to write the energy equation for the open feed water heater, it's similar to a heat exchanger. Okay, so all you have to do is to perform the energy balance. You have some fluxes coming in and other fluxing getting out. So the equation of a heat exchanger is sum of m dot n hn equals to sum of m dot out h out. Okay, because you know, here for a heat exchanger, you don't have a work done on the system or by the system, and the heat exchanger is well insulated from the surrounding in general. So you only have, if you want, internal exchange of heat. This is why the energy balance will be reduced to sum of m dot in hn equals to sum of m dot out h out.
Doctor, so Q and W are both zero in the heat
Exactly. In
exchanger.
the general, if you start from the general energy equation, you don't have Q, because here Q dot, when you say Q dot control volume, it means that you are computing the heat rate between the heat exchanger and the surrounding. The heat exchanger in general is well insulated. Why? Because what you need to do is you want to mix, or you want to exchange heat between two streams, let's say. Or here you can, here you have two inlets and one outlet, and you are mixing your fluid to so that it can exit at a certain new final temperature. Okay, so here it's, when we say open feed water heater, it's an open chamber where you mix these two flows to just have one outlet at the end. And if you are talking about boiler or condenser, for example, let's say, also boiler and condensers are heat exchangers. But whenever you write for your boiler the equation, you just consider as control volume the fluid circulating. Okay, but if you want to treat the boiler as a heat exchanger, at the end, what is happening in the boiler? In the boiler, you have two, let's say you have the fluid that is entering and exiting, and you have another stream For example, let's say in a electric power plant, you can have hot gases, let's say. These hot gases that you can bring them from cogeneration or from any, let's say if you are burning fuel, the combustion gases will enter the heat exchanger, okay? And you will take heat from these combustion gases and provide this heat to the fluid circulating in the boiler. So if you take a system, if you want the whole boiler, the whole boiler will not have Q dot with the surrounding. You will just have exchange between the two, the combustion gases and the fluid. But now, when we write in our problem, when we take with the control volume just the fluid stream of interest in the cycle, in this case, we say that we have Q dot N, because Q dot N will come from the combustion gases. Okay? So here, when you take the whole open feed water heater as system, it's a heat exchanger, and this heat exchanger will not interact with the surrounding. You have good insulation, so Q dot with the surrounding is 0, and you don't have any work. You don't have expansion. You don't have compression. Okay, so in this case, you can say that within your heat exchanger, you are mixing fluids. You have a condition at inlet, and after mixing, you'll get a new condition at outlet based on the conservation of energy balance. So here we can write that. What is the mass flow rate coming from the turbine? We said that we called it Y, okay? And the mass flow rate coming from the pump is 1 minus Y. While the exit flux will be the summation of these two, yani Y plus 1 minus Y, it is equal to 1. So if I want to write the energy equation, I say m dot of this inlet. So this inlet is characterizing 0.6. So I go to the table, thermodynamic table, and I find what is, let's say, H6. I can put that m dot 6 times H6. And m dot 6, as we said, is Y kilogram per second. Plus, this point is 0.2, okay? So plus m dot 2 H2. And as we mentioned, m dot 2 is 1 minus Y, is equal to the summation of the flow rates m dot 2 and m dot 6, which is 1, times the enthalpy at the exit of the heat exchanger, which is the characteristic 0.3, so equals to H3. So this is the energy governing what is happening in the open feed water heater. And now let me go back to my cycle, how to characterize the different points, okay? In general, what they will give you in this problem, they can give you 3 pressures. Yani they will tell you, they will give you what is P low, okay? What is P intermediate, which is if you want the pressure at which you have the mixing in the open feed water heater. So here you have P intermediate. And you have P high. So this will be given in general for you, okay? And let's say we know these properties. We start from 0.1, okay? Let us say we know that 0.1 is saturated liquid, okay? We know what is P low. We go to the table of saturated liquid. We get the value of H1, and we get the value of specific volume, V1. Now, between 1 and 2, what is the characteristic? From 1 to 2, okay, we have the pumping process. So what will happen? You'll have elevation of a pressure, okay? We go from P low to P intermediate. And since the process is isentropic, so it's characterized by S1 equals to S2. So now we know S2, and we know the intermediate pressure P2. So we know S2 and we know P2. Then we can go to tables, okay, in order to determine what is the value of H2. If you remember in the problems we discussed together that sometimes in case you have let's say it's the compressed liquid state.
Fluid.
Yes, sometimes in the tables you don't have this point, and you don't find it in the compressed tables. So you can do let's say the assumption, for example, you can take the value as the value at saturated liquid. In case, for example, when you want to compute, let's say, the work done by the pump from 1 to 2, you have the right, okay, to say because it's in compressed liquid region, I can consider when I do the formula, we know that the value of the work for during the pumping process, okay, can be computed as V delta P, okay, and you can assume then if you don't have the compressed tables to give you state 2, you can just say I can use W pump equal V delta P, where the specific volume is considered. We can consider that V1 and V2 are nearly equal, because you know that it's not easy to change. You need to change the specific volume of a liquid. You need a very large variation of pressure. That's why it's a good assumption to take that V1 is equal to V2. And then you can find the work of the pump. And once you find the work of the pump using this formula, you can say that it's equal to H2 minus H1. So you can calculate the value of H2. So this is how, in general, we find the enthalpy of 0.2 in case we don't have it in the tables, in the compressed tables. Okay. Now, we are done with state 2. Okay. We know now what is the value at state 2. Now, what we will go now to what is new in this problem, if you want, is state 3. Okay, state 3, because what we are doing now, we are taking from the turbine we are extracting a part of the steam, and we are also mixing it with the exit of pump 2. So here we can correlate, if you want, we can find a relation between points 2, 6, and 3. And 3, in general, point 3 will be, we can determine it. We know it. Why? Because it will be on the saturated liquid zone. Okay, so for point 3, you know the value of P intermediate. It will be given for you. And you say, since point 3 is saturated liquid, okay, because I will mix these two anyway to exit as saturated liquid. So this is known for the case of regenerative Rankine. All of this information, of course, will be clearly stated for you in the given. Okay, so since 3 is saturated liquid and we know the intermediate pressure, then we can also find the value of H3. Okay, and knowing the value of H3, we can determine H4 in the same, exactly in the same way. Okay, because we know that we have a pumping process between points 3 and 4, and we can use that V3 is equal to V4. We can say that W, just please pay attention. Here, when you want to find W, okay, of the pumps, you know that we can find first W in kilojoule per kilogram. But if we want to find the value in kilojoule, we should multiply by the mass, okay? Because you know that when you do in general big W,
Professor?
m dot, okay, m dot times small w. So to get the value in power, so you know that at the end you need to calculate power in what, okay? You have the power is m dot, which is in kilogram per second, times the specific work, which is the specific work in terms, if you want, done, which is in kilojoule per kilogram. So when you multiply W by m dot, okay, then you can get the value in watt. And here we should pay attention that the mass flow rates are not the same in this cycle and in this one. Yani, when you go through pump 1, what is the flow rate? It's 1 minus y. Okay. While when you consider pump 2, in pump 2 you have the total flow rate, which is 1 going through pump 2. This is why when you want to compute, let's say, the network, okay, when you want to find the network, you should multiply W pump in by the coefficient, which is 1 minus y, and W pump 2 by 1, because you don't have same flow rates going through your system. Okay.
Professor,
Yes.
we're gonna get something like open feed water heaters for exam.
Okay. Look, what I want no, you will not get if you want this, but what I want you to know, in case I give you any, you can have, let's say, a new problem. Okay, but I will describe for you what you need to know in order to proceed for it. I can give it for you, but what is the condition? I will give you a description paragraph to tell you how it's working, and then once I describe for you, yes, you are responsible just of doing the analysis. Okay, but of course I don't expect that you know the system already. Okay.
All right. اليوم revision,
Yeah, revision. So look, this is a revision, but we are applying it on a new cycle, because if we will still repeat the same cycles, we're just repeating same things. So I want you, if you want, the procedure is the same. You can see that nearly the procedure is the same, but if I have a new component, I should know how to deal with it.
Deal.
Okay.
All right, thank you.
Okay, so here, for example, then after I determine point 3, I will be able, as we mentioned, to determine state 4, because the relation between 3 and 4 is, as we discussed, okay, we can find the corresponding work by saying it's V delta P, okay, and then and of course here it's P high minus P intermediate. So this is work, if you want to work in part 2, it's V times P high minus P intermediate. Okay, and we said that we can take the assumption that V3, this is V is equal to V3 equal to V4. Okay, and once we get the value of W2, we can calculate what can we calculate when we get W2?
The missing H.
H missing, exactly, which is H4. We can say that this is equal to H4 minus H3. Okay, so now we determine the state 4. Now what is happening? We are entering in the turbine, and we are entering, sorry, in the boiler, and you know that in the boiler you have heating at constant pressure. So at the exit of the boiler will have a superheated state. Okay, now what will determine if you want this point? They should give me a certain information. Hala, we'll do an example together. They should give me, for example, the exit temperature. If I know T exit, okay, I know T exit and I know the pressure, I can go to superheated tables to get the enthalpy at 0.5. So I determine the value of H5. And then I am entering my turbine. So in my turbine, I have expansion. But here, what is new, that when I reach, if you want, the point corresponding to the pressure line at the same S, of course, and what is common between 0.567 is what is S. So I can write that S of 0.5 is equal to S of 0.6 is equal to S of 0.7, because it's an isentropic process. So already you know that if you have two properties, you can determine all others. So from between 5 and 6, you have same S. And for 0.6, the pressure is P intermediate. So you can go to the superheated table to get the value of H6. While in general, for 0.7, you can have, you should, to know if it's inside the dome or not, you just go to the tables, to the saturated tables of water, and you check for P low. For P low, okay, you know, in general, you have a table that will give you what is S at point F, saturated liquid, and what is S at point G, which is saturated vapor. Okay, in case S5, which is equal to S6, equal to S7, is between SF and SG, so you have the case of mixture, and you can calculate the quality. So how we calculate the quality? The quality will be S at 0.7 minus SF over SG minus SF. So this equation will give you the value of the quality. And once you know the quality, you can find all other properties like enthalpy, for example. Here, you are interested in getting the enthalpy at 0.7. So you can apply this relation. So you can say H7 minus H at point F over Hg minus Hf is equal to X. Okay, and since you have X, you get H of 0.7. So this is the procedure to find enthalpies of all points. Okay, and once I have all enthalpies, I am ready to answer the question of efficiency. My final purpose is to know the efficiency of this system. In order to determine the efficiency, I should go back, if you want, to the formula. We said that the efficiency is W net over Q dot N. Okay. Here, because we have several pumps, so in order to calculate W net, we know that we should take a plus W, it's plus W turbine, okay, minus W pumps. Because we have two pumps here, and we should get, if you want, the summation. So it's minus W pump 1 minus W pump 2. Okay, so now if we look at our figure here, first, for the turbine, if you want to compute the total work produced, you should pay attention that between 5.5 and 6, okay, what is the flow rate circulating from 5 to 6? Is it the whole flow rate? Okay, let us look at the again at the figure. Okay, the turbine, what is happening is the following. You have here the complete mass flow rate of 1 kilogram per second is coming from 0.5. Okay, now a part of it will be extracted in the to the open feed water heater. Okay, which is why. While the remaining part will be extracted to the condenser. Okay. And these two parts will mix again. Okay, in the open feed water heater before being pumped to the boiler, and the cycle will continue. Okay, so first, in the first expansion stage, yani before exiting at state 6, the whole amount, okay, the whole mass flow rate expanded from 0.5 to 0.6. So here the mass flow rate doing expansion from 5 to 6 is equal to the whole mass flow rate, which is, let's say, 1 kilogram per second. Okay. However, after this, a part it will be extracted and will go to the open feed water heater. And if I represent it here, the part going to the open feed water heater is this one. This is equal to Y. While the remaining part, okay, the remaining part will expand to until reaching the condenser. So the part that will expand from 6 to 7 is just 1 minus Y. And for this reason, when you evaluate the, if you want the output of the turbine, which is in kilojoule per kilogram, you should pay attention, okay, that only the fraction going from 6 to 7 is only 1 minus Y, while the fraction going from 5 to 6 is the whole flow rate, okay? This is why the value of W turbine output will be H5 minus H6 plus 1 minus Y times H6 minus H7, okay? On the other hand, if I consider now W net of pump, also I should consider W of pump 1 and W of pump 2. If I look at my figure, we know that in this part, the circulating flow rate is 1 minus Y of the total flow rate. So the part undergoing pumping process in pump 1 is only 1 minus Y. While for pump 2, the whole fraction will be considered, because at the exit of the open feed water heater, okay, you have the total flow rate that will exit, which is 1, and enter pump 1. That's why for W pump 2, you take the whole fraction, while for W pump 1, you only take 1 minus Y. Okay, and now once you compute what is, if you want W turbine, W pump, you can calculate W net. You still need to find, if you want, the expression of Qn, and Qn is, you know, it's within the boiler, and the whole flow rate will go through the boiler. So Qn is H5 minus H4, and now you will be ready to calculate the value of your efficiency. Okay, now we'll do a practical problem on this with numbers. So just you have to apply these equations and you will be able to solve for the efficiency of your system. And you can see that if you compare with a conventional Rankine cycle, that the presence of the open feed water